welcome to Sleep to Science. Tonight, we're diving into the most mysterious inhabitants of our cosmic neighborhood. Picture looking up at a peaceful night sky filled with twinkling stars. Everything appears calm and predictable, but scattered throughout space are invisible neighbors so powerful they control the fate of entire galaxies. What would you think if someone told you these cosmic phantoms actually built the universe we see today? They don't just destroy everything that gets too close. Instead, they carefully orchestrate star formation across billions of years. Tonight we'll discover how astronomers finally detected these invisible rulers. You'll see how they operate like cosmic construction managers. They shape galactic neighborhoods with mathematical precision. We'll explore why the universe's most extreme objects became its most essential architects. From Einstein's strangest predictions to the first photograph of something that absorbs all light, tonight's journey reveals how cosmic invisibility shapes everything visible. So settle in. Before we begin, leave a quick note in the comments, where you're listening from, or one thought you're carrying tonight. I read them, and they genuinely help shape future journeys. If you'd like more nights like this, subscribe, only if you enjoy these late-night journeys. Now let's begin. Something strange has been happening at the center of our galaxy. Astronomers noticed stars behaving very oddly in that region for decades. These weren't gentle planetary orbits like we see in our solar system. These stars were racing around at absolutely incredible speeds. Take star S2, for example. This cosmic speedster completes one full orbit every 16 years. It orbits around something astronomers couldn't see at all. When S2 reaches its closest approach, it accelerates to 7,000 kilometers per second. That's fast enough to circle Earth in about 6 minutes. Here's the really puzzling part. It appeared to be orbiting around completely empty space. What could grab hold of a massive star and make it dance like this? Only one possibility made sense. Something containing the mass of 4 million suns. All that mass compressed into a region smaller than our solar system. But this cosmic heavyweight remained completely invisible to every telescope pointed at it. It absorbed all light that came too close. Even the most powerful telescopes showed nothing but darkness where the gravitational center should be. The mathematics told an incredible story. For those orbital speeds to work, all that solar mass had to be concentrated in an impossibly small space. If you took 4 million copies of our Sun and squeezed them into Mercury's orbit, you'd create something with gravitational pull so intense that light itself couldn't escape. That's exactly what sits at our galaxy's heart. This invisible neighbor has been running galactic operations for billions of years. Every star you see at night ultimately responds to its gravitational influence. We don't just live near a black hole. We live inside a galaxy that's been shaped and controlled by one for its entire existence. Black holes aren't random destroyers floating around space. They're sophisticated galactic control centers. They manage star formation and basically run the show across hundreds of thousands of light years. Think of them as cosmic thermostats that keep entire galaxies operating at exactly the right temperature. Here's how this remarkable management system actually works. When material falls toward a supermassive black hole, it doesn't disappear quietly. Instead, it forms a swirling disk heated to millions of degrees. This cosmic blender becomes so energetic it launches jets of particles at nearly light speed. These jets blast outward across the entire galaxy. They carry energy equivalent to billions of suns and control whether new stars can form. It creates a fascinating cosmic conversation. When the black hole feeds heavily, it generates enormous amounts of energy. This heats surrounding gas clouds dramatically. The heating prevents new star formation, essentially putting the galaxy on a controlled diet. When feeding stops, things cool down and star formation resumes. This cycle has been operating for billions of years. What's truly remarkable is how precise this system works. Astronomers discovered that every large galaxy follows the same exact rule. The central black hole's mass always equals precisely 0.1% of all stars in the galaxy's central region. Always. This isn't coincidence. It's evidence that black holes in galaxies grow together like perfectly matched dance partners. Without this invisible management, galaxies would be disasters. Some would burn through star-making material too quickly and die young. Others would shut down completely and become stellar graveyards. Only galaxies with properly calibrated black holes maintain steady, controlled star formation. This creates stable neighborhoods where planets can form and life might develop. We're living inside a cosmic machine. It's been fine-tuned by its invisible manager for billions of years. The result creates exactly the kind of stable environment where creatures like us could eventually evolve to wonder about black holes in the first place. Here's something that sounds completely backwards. The universe's brightest objects are powered by its darkest ones. Scattered across cosmic distances, astronomers discovered beacons of light so brilliant they outshine entire galaxies containing hundreds of billions of stars. These cosmic lighthouses can be seen from billions of light years away, but they're actually powered by supermassive black holes. How does something that absorbs all light create the brightest beacons in the universe? The answer lies in what happens before matter crosses the point of no return. When a supermassive black hole begins actively feeding, surrounding material doesn't fall straight in. Instead, it forms what astronomers call an accretion disk, a cosmic whirlpool of gas and dust spiraling inward like water circling a drain. But this cosmic drain operates under extreme conditions. Friction within the swirling disk heats material to temperatures over 10 million degrees. That's hundreds of times hotter than our sun's core. At these temperatures, the disk glows brilliantly across the entire electromagnetic spectrum. X-rays, ultraviolet light, visible light. The accretion disk produces more energy than we can easily comprehend. The numbers are absolutely staggering. A typical quasar generates energy equivalent to 1 trillion suns burning simultaneously. Some exceed even this incredible output by factors of 10 or more. All this energy emerges from a region smaller than our solar system. It's the most efficient energy conversion process known to physics. Matter falling into a black hole converts about 40% of its mass directly into energy. Nuclear fusion manages only 0.7% efficiency by comparison. These cosmic lighthouses serve as beacons from the early universe. The most distant quasars we observe formed when the cosmos was less than 1 billion years old. Their light has been traveling toward us for over 13 billion years. When we study these ancient beacons, we're seeing how supermassive black holes operated when the universe was young and galaxies were still forming their basic structure. Einstein warned us that black holes would do impossible things to the fabric of reality itself. Near these cosmic giants, space stretches like taffy and time crawls to a near standstill. But these aren't just theoretical predictions anymore. Astronomers have actually measured these mind-bending effects occurring around real black holes. Close your eyes and imagine spacetime as a flexible rubber sheet. Place a bowling ball in the center and watch the sheet curve dramatically around it. Now imagine that bowling ball contains the mass of 4 million suns compressed into a space the size of a city. the rubber sheet doesn't just curve. It creates a gravitational well so deep that nearby objects have no choice but to follow its contours. This warping creates effects that seem to violate common sense. As objects fall toward a black hole, time itself begins to slow down relative to distant observers. An astronaut approaching the event horizon would appear to move in slow motion to someone watching from a safe distance. Near the black hole, their watch would tick normally from their perspective. But to external observers, seconds would stretch into minutes, then hours, then days. The effect becomes even more dramatic closer to the event horizon. Light leaving the falling astronaut would stretch to longer and longer wavelengths, shifting from white to red to infrared until it fades beyond detection. From the outside perspective, the astronaut would appear frozen in time at the edge of the black hole. They would slowly fade from view, but never quite disappear. Meanwhile, tidal forces would create another disturbing effect. Black holes don't pull uniformly on objects. The gravitational difference between your head and feet would become so extreme that you'd stretch like cosmic spaghetti. Astronomers call this spaghettification, probably the most unfortunately named process in all of physics. But here's what makes these effects truly remarkable. They're not science fiction anymore. Using precise timing measurements of pulsars orbiting black holes, astronomers have confirmed that time really does slow down in strong gravitational fields. It matches Einstein's prediction. Space really does warp around massive objects. The universe operates according to rules that challenge our everyday understanding of reality. Black holes didn't just passively watch the universe evolve. They actively participated in cosmic construction projects that span billions of years. Without these invisible architects, the cosmos would look completely different. Galaxies wouldn't exist in their current forms. Stars might not form at the regulated pace necessary for stable planetary systems. The universe might be a very different, much less hospitable place. Consider this remarkable timeline. Supermassive black holes appeared surprisingly early in cosmic history. Astronomers detect them operating when the universe was less than 700 million years old, just 5% of its current age. These ancient giants already contain billions of solar masses. They formed before most stars have time to live their entire life cycles and die. This suggests black holes played a fundamental role in cosmic evolution from the very beginning. The relationship between black holes and galaxy formation resembles a cosmic chicken and egg problem. Did galaxies form first and then grow black holes at their centers? Or did massive black holes form first and help gather surrounding material into galactic structures? Current evidence suggests they grew together through billions of years of mutual influence. Black holes regulate star formation rates through their feeding cycles. During active periods, they generate so much energy that they heat surrounding gas clouds and temporarily shut down star formation. During quiet periods, cooler conditions allow new stellar nurseries to form. This cosmic breathing pattern creates waves of star formation that spread outward through galactic neighborhoods over millions of years. They also help distribute heavy elements throughout cosmic space. When massive stars explode as supernovae, they scatter elements like carbon, oxygen, and iron, the building blocks necessary for rocky planets and complex chemistry. Black hole jets help transport these essential materials across vast distances, seeding future generations of stars and planets with the ingredients necessary for life. Perhaps most remarkably, black holes may have solved one of cosmology's biggest puzzles. The early universe contained much more star-forming material than we see today. Where did all that gas disappear to? Black hole feedback provides the answer. Over billions of years, their energy output heated and expelled enormous amounts of gas from galaxies, gradually transforming the cosmos from a dense, rapidly star-forming environment into today's more regulated, long-lived galactic neighborhoods. Not every star gets to become a black hole when it dies. The universe operates an extremely exclusive membership club for black hole formation. The entrance requirements are surprisingly specific. They're absolutely non-negotiable. Your star needs to weigh at least 25 times more than our Sun just to qualify for consideration. Anything smaller simply doesn't make the cut. Most stars in our galaxy are actually cosmic lightweights. Red dwarf stars barely tip the scales at 1/10 our Sun's mass. They burn their fuel so efficiently they'll outlast our Sun by trillions of years. These stellar marathon runners will fade away as white dwarfs when they eventually run out of fuel. No black hole transformation for them. Stars between 1 and 8 solar masses follow a different retirement plan. When they exhaust their nuclear fuel, they puff up into red giants. They shed their outer layers into beautiful planetary nebulae. Then they settle into white dwarf retirement. Stars between 8 and 25 solar masses go out with more dramatic flare. They explode as supernovae and leave behind neutron stars. These cosmic lighthouses pack the mass of our Sun into a sphere just 20 kilometers across. But the real heavyweights play by completely different rules. Stars exceeding 25 solar masses live fast and die spectacularly. They burn through their nuclear fuel like cosmic gas guzzlers. They exhaust their energy supplies in just a few million years instead of the billions our Sun will enjoy. When these stellar giants run out of fuel, they face a gravitational crisis that smaller stars never experience. The physics becomes absolutely relentless at this scale. When a more than 25 solar mass star collapses, no known force in the universe can stop the implosion. Nuclear fusion stops, providing outward pressure. The core temperature reaches billions of degrees. Gravity wins the ultimate cosmic tug of war. The star's core implodes so violently that protons and electrons get crushed together. This forms an infinitely dense point called a singularity. This cosmic transformation happens in less than 1 second. Imagine the universe's most dramatic weight loss program happening right now. In just 1/10 of a second, a stellar core containing more mass than our entire Sun collapses. It shrinks from the size of Earth down to an infinitely small mathematical point. No diet plan in human history comes close to this cosmic transformation. The collapse begins when nuclear fusion suddenly stops in the star's core. For millions of years, the outward pressure from fusion reactions balanced the inward pull of gravity. This cosmic standoff kept the star stable and shining. But massive stars burn through their fuel supplies like cosmic spendthrifts. Once the nuclear furnace shuts down, gravity takes complete control. What happens next challenges our everyday understanding of matter itself. The core temperature skyrockets to 100 billion degrees. That's about 6,000 times hotter than our Sun's core. At these extreme temperatures, atomic nuclei break apart completely. Protons and electrons get crushed together so violently they merge into neutrons. The normal structure of matter simply cannot survive this cosmic steamroller. During the final moments, the collapse accelerates to incredible speeds. The stellar core shrinks faster than a falling elevator in a skyscraper. But instead of falling a few hundred meters, this cosmic core falls inward on itself. Nothing can stop the implosion. The final stages happen so quickly that light cannot escape the collapsing region fast enough. It cannot carry away energy and slow down the process. The mathematics describing this collapse predict something that sounds impossible. All the matter in the stellar core gets concentrated into a region of zero volume. That's roughly 3 times the mass of our Sun. Physicists call this a gravitational singularity. It's a place where our normal understanding of space, time, and matter breaks down completely. The density becomes mathematically infinite. Surrounding this impossibly dense point, the collapsed star's gravity creates a boundary in spacetime itself. Nothing can escape from this boundary, not even light. Every black hole comes equipped with an invisible boundary. It operates like the universe's most secure prison system. Once anything crosses this cosmic point of no return, it can never return to the outside universe. Astronomers call this boundary the event horizon. It represents one of the most fascinating consequences of Einstein's theories made manifest in the real cosmos. The event horizon isn't a physical surface like a planet's crust or a star's photosphere. Instead, it's a mathematical boundary in spacetime itself. Think of it as the cosmic equivalent of a one-way mirror. Except this mirror works with gravity instead of light. Everything outside the event horizon can see objects falling toward the black hole. But once something crosses this boundary, it disappears from the outside universe forever. The size of this invisible boundary depends entirely on the black hole's mass. Stellar mass black holes created from collapsed massive stars have event horizons roughly 30 kilometers across. That's smaller than most major cities. Supermassive black holes lurking at galactic centers possess event horizons that could comfortably contain our entire solar system. The mathematical relationship is surprisingly simple. Double the black hole's mass, and you double the event horizon's radius. But here's where things get truly mind-bending. The event horizon creates different experiences for different observers. An astronaut falling past this boundary would notice nothing special about the crossing itself. From their perspective, they pass through empty space. They continue falling toward the central singularity. Their watch ticks normally. The stars overhead look essentially the same. However, anyone watching this cosmic mishap from a safe distance would witness something completely different. As the falling astronaut approaches the event horizon, they appear to slow down dramatically. This happens due to extreme gravitational time dilation. Their image becomes frozen at the boundary. It slowly fades from view as their light gets stretched to longer and longer wavelengths. To outside observers, the astronaut never quite seems to cross the event horizon. They simply fade away like a cosmic ghost, forever suspended at the edge of forever. Not all massive stars announce their death with explosive supernovae that light up entire galaxies. Some of the universe's most massive stars choose a completely different exit strategy. They skip the cosmic fireworks entirely. These stellar giants essentially vanish from the universe with barely a whisper. Astronomers call this process a failed supernova. During a typical supernova explosion, the collapsing stellar core bounces when it reaches maximum density. This cosmic rebound launches a powerful shockwave outward through the star's outer layers. The shockwave blasts them into space in a brilliant explosion visible across cosmic distances. The explosion disperses heavy elements forged in the star's core throughout surrounding space. This seeds future generations of stars and planets with essential building blocks. But stars exceeding roughly 40 solar masses face a different fate entirely. When these cosmic monsters collapse, their cores become so massive that even the supernova shockwave cannot escape. The imploding material simply keeps falling inward. It falls past the point where a normal explosion would occur. Instead of bouncing and exploding outward, everything falls past the newly formed event horizon. It disappears from observable reality. Astronomers discovered this silent death process by accident. They were monitoring massive stars in nearby galaxies. They noticed several extremely massive, bright stars that simply disappeared between observation periods. One day the star appeared normal in telescope images. The next observing session showed nothing. No explosion, no expanding gas cloud, no stellar remnant. The massive star had simply vanished as if someone had turned off a cosmic light switch. These direct collapse events actually create more massive black holes than typical supernovae. Instead of losing most of their mass during an explosive death, these stellar giants preserve nearly their entire mass. A 60 solar mass star collapsing directly might create a 50 solar mass black hole. The same star exploding as a supernova would leave behind a black hole containing only 10 to 15 solar masses. The universe's quietest stellar deaths produce its most massive stellar remnant black holes. Long before any stars formed, a completely different type of black hole formation was taking place. The universe was less than 1 billion years old. It was still figuring out its basic operating procedures. These primordial black holes didn't form from collapsing stars. Stars hadn't even been invented yet. Instead, they formed directly from the dense matter fluctuations left over from the Big Bang itself. During the universe's infancy, matter wasn't distributed evenly throughout space like it is today. Some regions were significantly denser than others. This happened due to random quantum fluctuations during cosmic inflation. In the densest regions, gravity could overcome the expansion of space itself. It collapsed these matter concentrations directly into black holes. No stellar intermediaries required. These ancient formation processes could create black holes across an enormous range of masses. Some primordial black holes might have contained only as much matter as a mountain. They were compressed into regions smaller than atoms. Others could have grown to masses exceeding modern supermassive black holes. This happened while the universe was still a cosmic toddler. The formation process operated like a cosmic lottery with completely unpredictable results. What makes primordial black holes particularly fascinating is their potential connection to modern cosmic mysteries. Dark matter makes up roughly 85% of all matter in the universe. But astronomers still haven't identified what dark matter actually consists of. Some theories suggest that primordial black holes could account for a significant fraction of this missing matter. They would be essentially invisible to our telescopes, but they would still exert gravitational influence on surrounding material. Recent gravitational wave detections have renewed interest in primordial black hole formation. When two black holes merge, they create ripples in space-time. Their masses often don't match what astronomers expect from stellar collapse scenarios. Some of these cosmic collisions might involve black holes that formed during the universe's first billion years. They're finally revealing themselves through their gravitational signatures. This happens billions of years after their ancient birth. Welcome to the cosmos's most secure detention facility. No prisoner has ever escaped. No rescue mission has ever succeeded. The security system operates so efficiently that even light itself cannot break out once it crosses the perimeter. The event horizon represents the universe's ultimate containment technology. It has maintained a perfect security record for billions of years. This cosmic prison operates on completely different principles than any earthly security system. There are no walls, no guards, no electronic surveillance systems. Instead, the event horizon uses the fabric of space-time itself as an impenetrable barrier. Once anything crosses this boundary, the geometry of space becomes so warped that all possible escape routes lead further inward. They all point toward the central singularity. The mathematics behind this containment system sound like science fiction, but they represent verified physics. At the event horizon, space itself flows inward faster than light can travel outward. Imagine trying to swim upstream in a river flowing faster than your maximum swimming speed. No matter how hard you stroke toward shore, the current carries you further downstream. Near a black hole, space itself becomes that inescapable current. Here's what makes this prison truly remarkable. The containment system scales automatically with the prisoner population. Add more mass to a black hole, and the event horizon grows proportionally larger. A black hole containing the mass of our Sun has an event horizon roughly 6 kilometers across. Double the mass, and the boundary expands to 12 kilometers. The universe's most massive black holes possess event horizons large enough to contain our entire solar system. The security measures become even more sophisticated for rotating black holes. These cosmic prisons create additional containment zones called ergospheres. These are regions where spacetime itself gets dragged around the rotating mass. Within the ergosphere, nothing can remain stationary relative to distant observers. Space itself rotates, carrying everything along like passengers on a cosmic merry-go-round. There's no way to step off the ride. Most remarkably, this ultimate security system requires no external power source. It needs no maintenance. The laws of physics themselves enforce the containment. No known force in the universe can break these cosmic shackles. Once the event horizon forms around collapsed matter, it operates as a permanent one-way membrane. It separates the black hole's interior from the rest of observable reality forever. At the very heart of every black hole lies something that challenges our understanding of reality itself. Physicists call it a gravitational singularity. It's a point where all the black hole's mass concentrates into zero volume. This creates infinite density and infinite gravitational curvature. It's a place where our most successful theories of physics simply give up and admit defeat. Normal matter cannot exist at a singularity. Atoms get crushed out of existence long before reaching this cosmic center. Protons and neutrons merge into exotic particles that may not follow any familiar rules. Even space and time lose their ordinary meaning near the singularity. The mathematical equations describing this region predict physical conditions so extreme that they exceed anything we can test or verify in laboratories. Scientists suspect that quantum effects become important at these scales, but no one knows exactly what happens when quantum mechanics meets extreme gravity. String theory suggests that singularities might actually be incredibly tiny vibrating loops of energy. Loop quantum gravity proposes that space itself has a granular structure that prevents true singularities from forming. These are educated guesses rather than established science. What makes singularities particularly puzzling is their relationship to information. If a library fell into a black hole, where would all the information contained in those books go? Classical physics suggests it disappears forever at the singularity. It gets completely removed from the observable universe. But quantum mechanics insists that information can never be truly destroyed. It might be scrambled or encoded in unrecognizable ways, but it must always remain recoverable in principle. The singularity also represents a boundary of scientific knowledge itself. Our most fundamental theories predict their own breakdown at this point. It's like having a map that says, "Here be dragons at the edges of explored territory." General relativity and quantum mechanics both succeed brilliantly in their respective domains, but they offer conflicting predictions about what happens at the singularity's infinite conditions. Perhaps most unsettling of all, the singularity exists in a region of space-time completely cut off from external observation. We can never directly study these cosmic mysteries, Any information about singularity physics cannot escape past the event horizon. The universe's most extreme physics experiments happen in perfect isolation. They remain forever hidden behind impenetrable gravitational barriers that make their secrets permanently inaccessible to outside observers. Despite their reputation as the universe's most complex objects, black holes obey remarkably simple mathematical relationships. You can calculate a black hole's size using basic arithmetic that any high school student could follow. The cosmic monsters that warp space-time and bend light follow rules so straightforward they seem almost anticlimactic. The key measurement is something called the Schwarzschild radius. It's basically the distance from the center to the event horizon. This cosmic boundary size depends entirely on the black hole's mass through an elegantly simple formula. Take the black hole's mass, multiply by a few physical constants, and out pops the answer. More mass equals bigger event horizon in a perfectly predictable way. For a black hole with our Sun's mass, the Schwarzschild radius works out to roughly 3 kilometers. That means the event horizon would sit about 3 kilometers from the central singularity. A black hole containing 10 solar masses would have its boundary at 30 kilometers from the center. The relationship stays linear. Double the mass, double the radius every single time. The numbers become truly staggering for supermassive black holes. The monster at our galaxy's center contains 4 million solar masses. This gives it an event horizon roughly 12 million kilometers across. That's large enough to comfortably fit the orbit of Mercury. Some supermassive black holes exceed even these dimensions by factors of hundreds or thousands. But here's the counterintuitive part about black hole density. Larger black holes are actually less dense than smaller ones. A stellar mass black hole crams several solar masses into a sphere a few kilometers across. This creates densities trillions of times greater than atomic nuclei. Meanwhile, a supermassive black hole spreads millions or billions of solar masses across regions comparable to planetary orbits. The average density inside a supermassive black hole's event horizon can be less than water. This simple mathematical relationship also reveals something profound about the nature of black holes. The event horizon size depends only on mass, not on the original star's composition, rotation rate, magnetic field strength, or any other detailed properties. All that information gets erased during gravitational collapse. Einstein's theory predicts that black holes have no hair. This means they can be completely described by just 3 numbers: mass, electric charge, and rotation rate. When massive stars collapse into black holes while spinning, they create some of the universe's most exotic gravitational environments. These rotating black holes don't just warp space. They drag spacetime itself into rotation like cosmic washing machines operating on the fabric of reality. The physics becomes so bizarre that stationary objects become impossible near these spinning gravitational monsters. Rotating black holes create a region called the ergosphere. Physicists call them Kerr black holes after the mathematician who first described them. Inside this cosmic washing machine zone, space itself gets pulled along by the rotation. Everything must rotate in the same direction as the black hole, whether it wants to or not. Space itself becomes a moving sidewalk that carries all matter and energy along for the mandatory cosmic ride. The ergosphere extends beyond the event horizon like an additional gravitational influence zone. Objects can still escape from the ergosphere if they have sufficient energy, but they cannot remain motionally stationary relative to distant observers. The dragging effect becomes so strong that even light beams get swept along by the rotating spacetime. Photons trying to travel opposite the black hole's rotation make no forward progress. They're like runners on a cosmic treadmill set to maximum speed. This frame dragging effect creates opportunities for what physicists call the Penrose process. It's a theoretical method for extracting energy directly from a rotating black hole. Objects entering the ergosphere at the right angle and velocity could theoretically split apart. One piece falls into the black hole while the other escapes with more energy than both pieces originally possessed. The extra energy comes from the black hole's rotational motion itself. Real rotating black holes likely spin at significant fractions of their theoretical maximum rotation rate. A black hole spinning at maximum speed would have its event horizon nearly touching the ergosphere at the equator. At this extreme rotation rate, the black hole becomes ablate. It gets flattened at the poles and bulges at the equator like a cosmic pancake, rather than a perfect sphere. The most remarkable aspect of rotating black holes involves their potential connection to cosmic jets. When matter falls into rotating black holes, magnetic field lines threading the ergosphere can get twisted into helical configurations. These launch powerful jets of particles along the rotation axis. These cosmic particle accelerators can shoot material outward at nearly light speed. They create some of the most energetic phenomena observable in the universe. What would actually happen if you took the ultimate cosmic plunge into a black hole? The journey would challenge every assumption about space, time, and reality itself. Your descent would become a masterclass in extreme physics. It would demonstrate effects so bizarre they seem like elaborate practical jokes played by the universe on unsuspecting visitors. The adventure begins well before crossing the event horizon. As you fall inward, you'd notice something called gravitational time dilation becoming increasingly dramatic. Your wristwatch would tick normally from your perspective, but outside observers would see your watch running slower and slower as you approach the point of no return. Near the event horizon, seconds on your watch would correspond to hours for distant observers. Then comes the cosmic stretch treatment that physicists call spaghettification. The gravitational difference between your head and feet would grow increasingly pronounced during your fall. For stellar mass black holes, this tidal stretching becomes lethal long before you reach the event horizon. You'd experience the universe's most extreme chiropractic adjustment. Gravitational forces literally pull you apart lengthwise while squeezing you from the sides. But the really mind-bending effects happen after crossing the event horizon. Inside this boundary, the normal relationship between space and time gets completely scrambled. The direction toward the central singularity becomes time-like rather than space-like. This means that falling toward the singularity becomes as inevitable as moving forward through time. You can no more avoid the singularity than you can prevent next Tuesday from eventually arriving. For rotating black holes, the interior journey becomes even more exotic. Instead of falling straight toward a point singularity, you'd encounter a ring-shaped singularity. There's potentially navigable space both inside and outside the ring. Some theoretical calculations suggest that the interior of rotating black holes might connect to other regions of spacetime. These cosmic tunnels are called Einstein-Rosen bridges or wormholes. The ultimate destination remains mysterious even to theoretical physicists. As you approach the singularity, tidal forces would grow to infinite strength. Space and time would lose their familiar meanings. The laws of physics would break down completely. Whether you'd be crushed out of existence, transformed into exotic matter, or translated to some other realm of reality, no one knows. It remains one of the deepest unsolved puzzles in science. Your cosmic adventure would end where mathematics itself admits defeat. Black holes operate the universe's most efficient heating systems. When matter starts falling toward these cosmic furnaces, it doesn't just disappear quietly into the gravitational abyss. Instead, it forms a swirling disk of material that gets heated to temperatures exceeding 10 million degrees. That's hundreds of times hotter than our sun's core. This cosmic heating system is called an accretion disk. It transforms ordinary gas and dust into one of the hottest environments in the known universe. The heating mechanism works through simple friction, but on a cosmic scale that produces extraordinary results. As material spirals inward toward the black hole, different layers of the disk rotate at different speeds. Inner regions orbit faster than outer regions. This creates shearing forces between adjacent layers. This cosmic friction generates tremendous amounts of heat. It's similar to how rubbing your hands together creates warmth, except amplified to astronomical proportions. The temperatures achieved in these cosmic furnaces depend on the black hole's mass. Smaller black holes create more compact, hotter accretion disks. Their event horizons lie closer to the central mass. A stellar mass black hole can heat its accretion disk to over 100 million degrees. Meanwhile, supermassive black holes create larger, somewhat cooler disks that typically reach temperatures of several million degrees. Still hot enough to strip electrons from atoms and create a glowing plasma brighter than entire star clusters. These cosmic heating systems operate with remarkable efficiency. An accretion disk converts roughly 10% of infalling matter's rest mass directly into energy through gravitational heating. Compare that to nuclear fusion in stellar cores, which manages only 0.7% efficiency. Black hole accretion disks represent the most efficient energy conversion processes known to physics. A single gram of matter falling into a black hole releases more energy than burning several tons of coal. The disks don't just produce heat. They create spectacular light shows visible across cosmic distances. The superheated plasma glows brilliantly in X-rays and ultraviolet light. These cosmic beacons can outshine their host galaxies by factors of hundreds or thousands. Astronomers can detect active black hole accretion disks from billions of light years away. This makes them some of the most luminous objects in the observable universe. Some black holes don't just swallow everything that gets too close. They also operate as cosmic fire hoses. They launch jets of particles outward at nearly the speed of light. These relativistic jets extend for thousands of light years beyond the black hole itself. They create some of the most spectacular fountain displays in the universe. The jets carry more energy than entire stellar explosions. They can reshape galactic environments across vast distances. The jet formation process involves a cosmic collaboration between the black hole, its accretion disk, and powerful magnetic fields. As material spirals inward through the disk, it generates electric currents that create magnetic field lines threading through the plasma. These field lines get twisted and amplified by the disk's rotation and the black hole's gravitational effects. Eventually, they form helical magnetic structures that act like cosmic particle accelerators. The magnetic field lines become so twisted they essentially turn into cosmic railguns. Charged particles get caught in these magnetic structures. They get accelerated to incredible speeds along the black hole's rotation axis. The particles shoot outward in two narrow beams. One beam emerges from each pole of the black hole system. These jets maintain their tight focus across distances that span entire galactic neighborhoods. They're like cosmic searchlights that never spread out or dim significantly. What makes these jets truly remarkable is their speed and power output. The particles race outward at velocities exceeding 99% the speed of light. Some jets carry energy equivalent to the total output of millions of stars combined. When these cosmic fire hoses encounter gas clouds or stellar material in their path, they create spectacular shock waves and heating effects. These can trigger or suppress star formation across entire galactic regions. The jets also demonstrate the black hole's influence extending far beyond its immediate gravitational reach. The event horizon might measure only a few kilometers across for stellar mass black holes. Yet their jets can extend for thousands of light years. That's millions of times larger than the black hole itself. These cosmic fountains represent the universe's most dramatic example. They show how compact objects can influence environments across distances that dwarf even large star clusters. When an ordinary star wanders too close to a supermassive black hole, it experiences the universe's most extreme makeover. The gravitational forces don't affect the star uniformly. Instead, they create a cosmic stretching effect that astronomers call tidal disruption. The star gets pulled apart like cosmic taffy. This creates long streams of stellar material that spiral around the black hole in a process so visually distinctive that scientists nicknamed it spaghettification. The physics behind this stellar destruction involves differential gravitational forces acting across the star's diameter. The side of the star facing the black hole experiences much stronger gravitational pull than the far side. This difference in gravitational strength gradually overwhelms the star's own gravity. Star gravity normally holds all the stellar material together in a cohesive ball. As the star ventures closer to the black hole, these tidal forces grow exponentially stronger. The stretching process happens gradually at first, then accelerates dramatically during the final approach. The star becomes elongated along the line connecting it to the black hole. It resembles a cosmic egg that gets progressively more stretched. Eventually, the tidal forces exceed the star's gravitational binding energy. Stellar material begins streaming away from both ends of the elongated star. The cosmic pasta machine has successfully converted a normal spherical star into long strands of hot gas. What happens to the stellar spaghetti depends on the star's trajectory and the black hole's mass. About half the disrupted stellar material typically gets captured by the black hole. It forms a new accretion disk. This sudden influx of fresh fuel can cause previously quiet black holes to flare up dramatically. They create brilliant outbursts of radiation that announce the stellar meal to astronomers across cosmic distances. The other half of the stellar material gets flung outward at high speeds. It escapes the black hole's gravitational influence entirely. Astronomers have observed several dozen tidal disruption events during the past decade. These cosmic meals produce characteristic light signatures that help scientists study both the disrupted stars and the black holes doing the disrupting. Each stellar spaghettification event provides valuable information about supermassive black hole masses, feeding behaviors, and the dynamics of matter under extreme gravitational conditions. The universe's cosmic pasta makers offer astronomers rare opportunities to watch black hole feeding in real time. When two black holes spiral together and merge, they create the most violent events in the universe since the Big Bang itself. These cosmic collisions don't just destroy the individual black holes. They literally shake the fabric of space-time. They send gravitational waves rippling outward at light speed like cosmic earthquakes that make the entire universe ring like an enormous bell. The merger process builds up over millions of years as two black holes gradually spiral closer together. They're locked in a gravitational dance of death. As they approach their final moments, the orbital speeds increase dramatically. During the last few seconds before collision, The black holes whip around each other hundreds of times per second. They radiate enormous amounts of energy as gravitational waves. The space-time distortions become so intense they carry away several solar masses worth of energy in pure gravitational radiation. The actual collision happens faster than you can blink. In roughly 1/10 of a second, two individual black holes merge into a single, larger black hole. At peak, they can release more power than all the stars in the observable universe combined. But this energy doesn't emerge as light or heat. Instead, it propagates as ripples in space-time itself. These ripples stretch and compress the fabric of reality as they pass through. These gravitational waves travel across cosmic distances, essentially unimpeded by matter or energy. Unlike light, which gets absorbed or scattered by dust clouds and stellar material, gravitational waves pass through everything. They're like ghostly cosmic messengers carrying information about their violent birth events. When they finally reach Earth after journeys lasting billions of years, they cause incredibly tiny distortions in spacetime. These distortions are smaller than 1,000th the width of a proton. Detecting these cosmic earthquakes required some of the most sensitive instruments ever built. The Laser Interferometer Gravitational Wave Observatory uses laser beams traveling along 4-kilometer arms to measure spacetime distortions caused by passing gravitational waves. When LIGO first detected black hole mergers in 2015, it opened an entirely new window for studying the universe. Scientists can now hear cosmic events that produce no visible light. This reveals hidden populations of black holes and provides direct tests of Einstein's predictions about gravity's most extreme behavior. Each detected merger tells a story about black hole formation, evolution, and cosmic population statistics. The universe appears to be filled with merging black hole pairs. They create a constant background of gravitational wave signals that LIGO and similar detectors around the world continue discovering. These cosmic bells ring continuously throughout space. They announce violent events happening in distant galaxies and provide astronomers with a completely new way to study the universe's most extreme objects. Black holes create the most powerful particle accelerators in the known universe. They launch individual particles to energies that dwarf anything achievable in human-built laboratories. These cosmic accelerators operate continuously in space. They produce particles with energies millions of times greater than the Large Hadron Collider. They require no external power source beyond the black hole's own gravitational and magnetic environment. The acceleration happens in regions where black holes interact with surrounding magnetic fields and plasma. As material falls toward a black hole through its accretion disk, it creates powerful electric and magnetic fields. These fields can trap and accelerate individual particles to incredible speeds. Some particles get caught in magnetic field loops that act like cosmic particle tracks. They gain energy with each orbit until they reach velocities approaching light speed. The most energetic particles escape these cosmic accelerators as high-energy cosmic rays that travel throughout the galaxy and beyond. These particles carry energies equivalent to cosmic baseballs traveling at nearly light speed. When they eventually collide with Earth's atmosphere, they create particle showers containing billions of secondary particles. These rain down on the planet's surface. Some cosmic ray particles possess so much energy that scientists still debate exactly how natural processes could accelerate them to such extreme velocities. Black hole jets serve as particularly efficient particle acceleration zones. The magnetic field structures threading through these cosmic fire hoses create ideal conditions for what physicists call Fermi acceleration. This is a process where particles bounce back and forth between magnetic field irregularities. They gain energy with each interaction like cosmic pinballs in an electromagnetic game. The particles can spend thousands of years bouncing around within jet structures. They gradually build up enormous energies before finally escaping into intergalactic space. These natural particle accelerators help solve cosmic mysteries while creating new ones. High-energy particles produced near black holes contribute to the cosmic ray background that permeates our galaxy. They also generate neutrinos. These are nearly massless particles that barely interact with matter. They can travel straight through entire planets without slowing down. Some of the most energetic neutrinos detected on Earth likely originated from particle acceleration processes occurring near distant supermassive black holes. The universe's ultimate particle accelerators operate on scales and energy levels that human technology cannot match. While the Large Hadron Collider accelerates particles through a 27-kilometer tunnel, black hole acceleration zones can extend across light-years of space. These cosmic laboratories provide natural experiments in high-energy physics. They reveal how matter behaves under conditions impossible to recreate artificially. Stellar mass black holes represent the working class of the cosmic gravitational community. These compact neighbors contain anywhere from 3 to 20 times our Sun's mass. They're squeezed into regions roughly 10 to 60 kilometers across. They live relatively quiet lives scattered throughout galactic neighborhoods. Most of the time, they mind their own gravitational business without causing too much cosmic drama. You wouldn't even notice they're there. These suburban black holes formed from the collapsed cores of massive stars. Those stars once burned brightly in stellar nurseries. After their dramatic formation through supernova explosions or direct collapse, they settled into retirement. Now they serve as gravitational seniors of their local stellar communities. Unlike their attention-seeking supermassive cousins at galactic centers, stellar mass black holes prefer peaceful anonymity. They stay in cosmic neighborhoods far from the downtown action. The daily routine of a typical stellar mass black hole involves mostly waiting around. They wait for something interesting to fall their way, without active feeding from nearby stellar companions or wandering gas clouds. These cosmic retirees remain essentially invisible. They don't generate brilliant accretion disks or shoot out powerful jets. They simply sit quietly in space, warping local space-time geometry. Meanwhile, they patiently orbit around the galactic center like any other well-behaved stellar citizen. When stellar mass black holes do get active, it's usually because they've acquired a stellar companion through cosmic dating. Binary systems containing one normal star and one black hole can create spectacular X-ray sources. Material transfers from the living star to its gravitational partner. The infalling stellar material forms a hot accretion disk that glows brilliantly in high-energy radiation. This temporarily transforms the quiet black hole into a cosmic beacon visible across galactic distances. Most stellar mass black holes probably spend their entire multi-trillion-year lifespans in splendid isolation. They formed when the universe was young and star formation rates were much higher than today. As galaxies age and produce fewer massive stars, the population of stellar mass black holes becomes essentially fixed. These cosmic suburbanites represent a permanent resident population. They will continue their quiet gravitational existence long after all normal stars have exhausted their fuel and faded away. Intermediate mass black holes occupy the cosmic equivalent of middle management positions. They contain roughly 100 to 100,000 solar masses. These mid-sized gravitational executives should logically exist between stellar mass and supermassive black holes. But they've proven remarkably good at hiding their corporate headquarters. Astronomers have spent decades searching for definitive examples of these cosmic middle managers with frustratingly limited success. The mystery deepens when you consider that intermediate mass black holes should be relatively common based on theoretical predictions. If stellar mass black holes grow by accumulating matter over billions of years, some should naturally evolve into intermediate mass ranges. They would do this before eventually reaching supermassive status. Similarly, if supermassive black holes formed through gradual growth from smaller seeds, those seeds probably started as intermediate mass objects during the early universe. Recent astronomical detective work has uncovered a few potential hiding spots for these elusive cosmic executives. Dense star clusters called globular clusters represent prime real estate for intermediate mass black hole headquarters. These ancient stellar communities contain hundreds of thousands of stars packed into regions only a few light years across. The extreme stellar density could facilitate black hole formation and growth through direct stellar collisions and mergers. Some globular clusters show subtle evidence of central mass concentrations. These could indicate intermediate mass black holes lurking at their hearts. Stars in the cluster cores move faster than expected based on visible stellar masses alone. This excess velocity suggests additional invisible mass. It's possibly a cosmic middle manager operating from a gravitational corner office at the cluster center. Ultraluminous X-ray sources in nearby galaxies provide another line of evidence for intermediate mass black holes. These cosmic beacons shine too brightly to be powered by stellar mass black holes using standard accretion physics. But they're not quite luminous enough to definitively require supermassive black holes. They occupy the perfect luminosity range expected for intermediate mass black holes feeding on surrounding stellar material. The search for cosmic middle management continues as astronomers develop more sensitive detection techniques. These mysterious objects could hold crucial clues about how supermassive black holes formed and evolved during the early universe. Finding intermediate mass black holes would help complete the cosmic corporate hierarchy. It would reveal the full range of gravitational executives operating throughout galactic neighborhoods. Supermassive black holes represent the ultimate cosmic corporate executives. They contain anywhere from 1 million to tens of billions of solar masses. These gravitational CEOs operate from premium galactic downtown real estate. They run vast stellar empires from their executive suites at galactic centers. Their influence extends across hundreds of thousands of light years. They make every important decision about galactic development, star formation policy, and cosmic neighborhood management. The scale of these cosmic corporations defies easy comprehension. A typical supermassive black hole contains 10 million solar masses concentrated into a region smaller than our solar system's orbit. The most massive cosmic CEOs discovered so far exceed 60 billion solar masses. That's roughly 15,000 times more massive than the black hole at our own galaxy's center. These ultimate gravitational executives command corporate empires that dwarf anything in the stellar mass small business sector. Supermassive black holes didn't start at the top of the cosmic corporate ladder. They built their empires through billions of years of aggressive expansion, mergers, and acquisitions. When two galaxies merge, their central supermassive black holes eventually spiral together. They combine their assets into even larger cosmic conglomerates. These gravitational merger deals create the universe's most massive objects. They simultaneously reshape entire galactic neighborhoods. The corporate headquarters of supermassive black holes extend far beyond their event horizon office buildings. Their sphere of influence encompasses vast regions around galactic centers. Their gravitational policy decisions determine local star formation rates, gas circulation patterns, and overall galactic economic activity. Through their feeding cycles and jet emissions, these cosmic CEOs regulate the pace of galactic development. They do this with precision that would impress any earthly executive board. What makes these gravitational executives truly remarkable is their longevity and stability. While stellar mass black holes operate like small family businesses that rarely interact with neighbors, supermassive black holes function as permanent galactic institutions. They've been managing their cosmic territories for over 13 billion years. They maintain consistent corporate cultures while adapting to changing galactic economic conditions. The universe's most successful enterprises operate on timescales that span entire cosmic epochs. Black holes live completely different lives depending on their mass class. They're like cosmic residents segregated into distinct social neighborhoods with virtually no overlap in daily routines or social circles. The gravitational lifestyle gap between stellar mass and supermassive black holes resembles the difference between rural small-town living and urban corporate headquarters management. Stellar mass black holes lead solitary lives focused on local gravitational affairs. They typically experience feeding opportunities only when binary stellar companions transfer material. Sometimes occasional gas clouds drift within their modest gravitational reach. These feeding events last for relatively short periods, maybe decades or centuries before returning to quiet dormancy. Their accretion disks, when they exist at all, operate like small-scale cosmic diners. They serve individual customers rather than large institutional cafeterias. Supermassive black holes operate on completely different scales of cosmic interaction. Their gravitational reach extends across thousands of light years. This allows them to influence entire galactic regions simultaneously. They feed continuously on streams of gas flowing inward from galactic neighborhoods. They maintain massive accretion disk operations that can outshine their host galaxies. These cosmic restaurants can operate for millions of years at a stretch. They serve billions of customers across vast galactic territories. The environmental impact also varies dramatically between mass classes. Stellar mass black holes affect their immediate stellar neighborhoods through gravitational influence and occasional X-ray outbursts. When they become active, the effects remain localized within a few light years of their position. Meanwhile, supermassive black holes reshape entire galactic ecosystems. They do this through their feeding cycles, jet emissions, and gravitational regulation of star formation. Their influence spans hundreds of thousands of light years. Even their formation histories follow different social mobility patterns. Stellar mass black holes represent first-generation cosmic citizens formed from individual stellar collapse events. They rarely grow significantly after formation unless they happen to acquire long-term binary companions. Supermassive black holes, by contrast, built their massive status through cosmic social climbing. They grew continuously through accretion and mergers over billions of years. Eventually, they achieved ultimate gravitational executive status. The rotation rates also reflect their different lifestyle demands. Stellar mass black holes often spin rapidly because they inherited angular momentum from their progenitor star's rotation. Supermassive black holes typically rotate more slowly. They've accumulated material from multiple sources with randomly oriented angular momentum vectors. The cosmic executives operate with more measured, deliberate rotation befitting their institutional responsibilities. Meanwhile, stellar mass black holes spin like cosmic entrepreneurs running energetic small businesses. our Milky Way galaxy harbors a surprisingly large population of black holes. They're distributed throughout its stellar neighborhoods like a hidden cosmic demographic. Census takers are only beginning to count them accurately. Current estimates suggest our galactic home contains roughly 100 million stellar mass black holes. This makes them about 1,000 times more common than visible neutron stars or white dwarf remnants. This vast black hole population remains mostly invisible because the majority lead solitary lives. They lack stellar companions to provide accretion material. Only about 1% of galactic black holes currently emit detectable X-ray signatures from active feeding. The other 99% drift silently through space like cosmic ghosts. They reveal their presence only through gravitational influence on nearby objects or rare interactions with passing material. The distribution pattern follows galactic demographics quite predictably. Black hole concentrations peak in regions where massive star formation occurred most actively during the galaxy's youth. The galactic bulge and inner disk regions contain higher black hole densities. They hosted more vigorous star formation during earlier cosmic epochs. Meanwhile, the outer galactic suburbs where we live contain more modest black hole populations. This reflects their quieter star formation histories. Recent gravitational wave detections have revolutionized our understanding of the galactic black hole census. Before LIGO started detecting black hole mergers, astronomers knew of only about 20 stellar mass black holes in our galaxy. They found these through X-ray observations of binary systems. Gravitational wave astronomy reveals that black holes exist in binary pairs much more frequently than previously suspected. Merger rates suggest thousands of black hole binaries throughout the galactic population. The cosmic demographics become even more interesting when considering black hole mobility within galactic neighborhoods. Stellar mass black holes receive velocity kicks during their formation through asymmetric supernova explosions. They also get kicks from gravitational wave recoil from binary mergers. Some black holes travel at speeds exceeding 100 kilometers per second relative to their birth locations. This means they've migrated significant distances across galactic regions during their multi-billion-year lifetimes. Perhaps most remarkably, our galaxy's black hole population represents a permanent resident community. They will outlast virtually every other cosmic citizen. While normal stars will exhaust their fuel and fade away over the next trillion years, stellar mass black holes will continue their gravitational existence essentially forever. They represent the ultimate galactic survivors. They're destined to inherit an empty galaxy after all the lights go out and all the stellar residents have departed to cosmic retirement. Catching invisible black holes requires some of the most creative detective work in astronomy. Since black holes absorb all light that gets too close, astronomers cannot simply point telescopes at them and take pictures. Instead, they have developed techniques borrowed from cosmic crime investigation. They watch for circumstantial evidence that reveals the gravitational perpetrators hiding in plain sight throughout galactic neighborhoods. The most reliable detection method involves looking for stellar partners behaving suspiciously. Many black holes exist in binary systems with ordinary stars. These stars orbit around their invisible gravitational companions. These stellar witnesses cannot help but reveal the black hole's presence through their own peculiar behavior. When a normal star orbits something massive and invisible, it creates a cosmic crime scene. Astronomers can analyze this scene from thousands of light years away. The evidence shows up in the star's motion patterns. Astronomers measure the stellar victim's orbital velocity using something called the Doppler effect. It is the same principle that makes ambulance sirens change pitch as they drive past. When the star moves toward Earth in its orbit, its light gets compressed to slightly bluer wavelengths. When it moves away, the light stretches to redder wavelengths. By tracking these color shifts over time, astronomers can map the star's entire orbital dance. The mathematics reveal the invisible partner's mass with surprising precision. Faster orbital speeds indicate more massive companions. When the calculations show a companion exceeding 3 solar masses but producing no visible light, astronomers have caught their gravitational suspect. Normal stellar remnants like white dwarfs or neutron stars cannot exceed certain mass limits. They would collapse into black holes if they tried. Any dark companion above those thresholds must be a black hole. Some stellar partners provide even more dramatic evidence. They transfer material to their black hole companions. Gas flowing from the normal star toward the invisible partner forms a hot accretion disk. This disk glows brilliantly in X-rays. These cosmic feeding sessions create some of the brightest X-ray sources in our galaxy. The stellar accomplices essentially spotlight their black hole partners during cosmic meal times. This makes detection relatively straightforward for X-ray telescopes orbiting above Earth's atmosphere. Taking the first photograph of a black hole required building a telescope the size of our entire planet. The Event Horizon Telescope project linked radio observatories from Hawaii to Antarctica. This created a virtual telescope with Earth-sized resolution capabilities. After years of preparation and data processing, astronomers finally captured the ultimate cosmic portrait in 2019. They photographed the shadow of the supermassive black hole at the center of galaxy M87. The photography challenge stemmed from black holes' incredible compactness relative to their cosmic distances. Even the largest supermassive black holes appear smaller than a golf ball would look from the distance of the Moon. No single telescope on Earth possesses sufficient resolution to photograph such tiny cosmic targets across intergalactic distances. The solution required coordination between multiple observatories spread across continents. All of them pointed at the same target simultaneously. The actual photograph shows something that initially seems anticlimactic. It is a dark circular shadow surrounded by a glowing ring of superheated material. But this seemingly simple image represents one of the most technically challenging photographs ever attempted. The dark shadow reveals the black hole's event horizon, silhouetted against the brilliant accretion disk behind it. Light from the disk gets bent around the black hole's curvature. This creates a cosmic backlight that makes the shadow visible. The glowing ring is not uniform. It shows bright spots and asymmetries that reveal the black hole's rotation and the dynamics of infalling material. The bottom portion of the ring appears brighter than the top. This happens because the black hole's rotation creates a cosmic searchlight effect. It amplifies light from material moving toward Earth, while dimming light from material rotating away. These subtle brightness variations encode information about the black hole's mass, spin rate, and feeding behavior. Perhaps most remarkably, the photograph confirmed Einstein's predictions about black hole appearance with startling accuracy. Computer simulations based on general relativity had predicted exactly this type of image decades before technology made the observation possible. The M87 black hole's shadow matches theoretical expectations so precisely that it provides one of the most dramatic confirmations of Einstein's century-old theory. The universe's most camera-shy objects finally revealed themselves to look exactly as the mathematics predicted. The supermassive black hole at our galaxy's center operates a cosmic NASCAR track. Stars race at mind-bending speeds around an invisible gravitational finish line. Astronomers have spent decades tracking these stellar speedsters. They use their orbital performances to measure the central black hole's mass with extraordinary precision. These cosmic race cars provide some of the most direct evidence for supermassive black holes anywhere in the universe. Star S2 holds the current galactic speed record. It reaches maximum velocities of 7,000 kilometers per second during its closest approach to the central black hole. That is fast enough to travel from New York to Los Angeles in about 40 seconds. This stellar Formula One champion completes its elliptical racetrack every 16 years. This provides astronomers with multiple opportunities to clock its performance and analyze the gravitational forces controlling its motion. The orbital analysis requires tracking stellar positions with incredible precision over many years. Astronomers use adaptive optics systems that compensate for atmospheric blurring. This allows ground-based telescopes to achieve nearly space-based image quality. They measure stellar positions accurate within a few millionths of an arcsecond. That is equivalent to detecting the width of a human hair from 500 kilometers away. This precision enables mapping of individual stellar orbits around the invisible gravitational center. Each star's orbital characteristics reveal different aspects of the central black hole's properties. The orbital periods depend on average distance from the gravitational center. Maximum orbital speeds indicate the central mass. Multiple stars following different orbital paths provide independent measurements. They all point to the same conclusion. A dark object contains 4.15 million solar masses. It is concentrated in a region smaller than our solar system's dimensions. The stellar speedway also revealed relativistic effects predicted by Einstein's theory. During S2's closest approach in 2018, astronomers detected gravitational redshift. The star's light got stretched to longer wavelengths as it climbed out of the black hole's deep gravitational well. They also measured orbital precession. The star's elliptical orbit slowly rotates around the central mass due to space-time curvature effects. These cosmic race cars provide natural laboratories for testing general relativity under extreme conditions impossible to recreate artificially. The universe rings like a cosmic bell every time two black holes crash together. They send gravitational waves rippling through space-time at light speed. These cosmic earthquakes remain completely invisible to traditional telescopes. But LIGO and similar gravitational wave observatories can detect the minute space-time distortions when they finally reach Earth. These distortions arrive after journeys spanning billions of years. Gravitational wave detection requires measuring length changes smaller than 1,000th the width of a proton. These measurements happen across detector arms stretching several kilometers. LIGO achieves this impossible precision using laser interferometry. Split laser beams travel down perpendicular arms, reflect off mirrors, and recombine to create interference patterns. When gravitational waves pass through the detector, they stretch space in one direction while compressing it in the perpendicular direction. This creates tiny shifts in the interference pattern. The cosmic earthquake signatures tell detailed stories about their violent origins. Black hole mergers produce characteristic chirp signals. These start at low frequencies and sweep upward as the orbiting black holes accelerate during their final death spiral. The frequency sweep reveals the masses of both black holes. The signal amplitude indicates how far away the collision occurred. Advanced data analysis can even extract information about the black hole's rotation rates and orbital orientations. LIGO's first detection in September 2015 opened an entirely new window for studying the universe. The signal came from two black holes containing roughly 30 solar masses each. They merged about 1.3 billion light-years away. The collision converted three solar masses into pure gravitational wave energy during the final fraction of a second. That is more power output than all stars in the observable universe combined. But this energy was carried by space-time ripples instead of electromagnetic radiation. Gravitational wave astronomy reveals hidden populations of black holes that remain invisible to optical and X-ray telescopes. Many detected mergers involve black holes with masses that do not match expectations from stellar evolution models. Some may be primordial black holes formed in the early universe. Others might represent exotic formation pathways not yet understood. These cosmic seismometers continue detecting new earthquakes regularly. They are building a census of black hole mergers happening throughout cosmic time. The universe's most violent events announce themselves through whispers in space-time that only the most sensitive instruments can hear. Black holes may absorb all light that crosses their event horizons, but their feeding activities create some of the most brilliant cosmic advertisements in the universe. When supermassive black holes actively consume surrounding material, they generate intense X-ray and gamma-ray emissions. These can be detected from billions of light-years away. These high-energy cosmic lighthouses help astronomers locate and study black holes across vast cosmic distances. The advertising mechanism works through superheated accretion disks that form when material spirals toward feeding black holes. Friction within these cosmic whirlpools heats the infalling matter to temperatures exceeding 10 million degrees. This causes it to emit brilliant X-ray radiation. The hottest regions near the black hole's event horizon produce gamma rays. These are the highest energy form of electromagnetic radiation. These cosmic beacons can outshine entire galaxies containing hundreds of billions of stars. X-ray telescopes orbiting above Earth's atmosphere serve as cosmic lighthouse spotters. They scan the sky for the characteristic high-energy signatures of active black hole feeding. Different types of black holes produce recognizable X-ray fingerprints. Stellar mass black holes in binary systems create rapid X-ray flickering. This happens as hot material orbits close to the event horizon. Supermassive black holes generate more steady X-ray emission punctuated by dramatic flares. These occur when they consume unlucky stars or gas clouds. The high-energy emissions also reveal details about black hole rotation and magnetic field structure. Rapidly spinning black holes can generate relativistic jets that produce gamma-ray emission. These jets extend thousands of light-years from the central engine. The jet emissions show up as cosmic searchlights that sweep across space as the black hole rotates. This creates lighthouse-like pulses detectable by gamma-ray telescopes. Perhaps most remarkably, these cosmic advertisements allow astronomers to study black holes during the universe's youth. This was when galaxies were still forming and growing rapidly. The most distant quasars are supermassive black holes feeding voraciously in early galactic cores. They appear as they existed over 13 billion years ago. Their light has been traveling toward Earth since the universe was less than 1 billion years old. These ancient cosmic lighthouses provide snapshots of black hole behavior during the cosmos's wild adolescent phase. They reveal how these gravitational giants helped shape galactic evolution across cosmic time. Albert Einstein never expected his mathematical equations to describe real objects in the universe. When he published general relativity in 1915, the theory predicted the existence of regions where gravity becomes so strong that space and time themselves break down. Einstein thought these solutions represented mathematical curiosities rather than physical realities. He famously wrote that such objects do not exist in physical reality. A century later, black holes have become Einstein's ultimate vindication. The theoretical foundation emerged from Carl Schwarzschild's work in 1916. This came just months after Einstein published his field equations. Schwarzschild solved Einstein's equations for the space-time around a perfectly spherical mass. He discovered that the mathematics predicted a critical radius where the equations become singular in Schild coordinates. This Schwarzschild radius represents the event horizon. It's a boundary where the escape velocity equals light speed and causality itself breaks down. Einstein remained skeptical about these mathematical monsters throughout his lifetime. The physical conditions seemed too extreme to exist in nature. How could matter compress to infinite density? How could space-time curvature become arbitrarily large? These solutions appeared to violate physical intuition so severely that they must represent mathematical artifacts rather than cosmic realities. Einstein preferred to believe that some unknown physical principle would prevent such extreme conditions from occurring. Modern observations have vindicated every major prediction of Einstein's reluctant theory. Black holes really do possess event horizons that trap light permanently. They really do warp space-time so severely that time dilation becomes extreme. They really do bend rays around their gravitational fields like cosmic magnifying glasses. The mathematical solutions that seemed impossibly exotic in 1915 describe actual objects scattered throughout our galaxy and beyond. Perhaps most remarkably, recent observations have confirmed Einstein's predictions with startling precision. The Event Horizon Telescope image of the M87 black hole matches computer simulations based on general relativity almost perfectly. Gravitational wave detections from merging black holes follow the mathematical waveforms predicted by Einstein's equations to extraordinary accuracy. The cosmic laboratories created by gravitational collapse provide the ultimate testing ground for general relativity. They test conditions impossible to recreate artificially. 2. The universe operates the most sophisticated physics experiments imaginable. It uses black holes as natural laboratories where Einstein's century-old mathematics describes reality with mathematical perfection. The reluctant theoretical predictions have become observational facts. They confirm that the cosmos really does operate according to principles so strange that even their discoverer couldn't believe they described physical reality. Time itself changes its pace near black holes. It runs slower and slower as you approach the event horizon until it nearly stops altogether from an outside observer's perspective. This isn't science fiction speculation. It's measurable reality that astronomers have now confirmed through precise observations of matter orbiting near supermassive black holes. The universe operates the ultimate time manipulation experiments using gravity as the controlling mechanism. The time dilation effect becomes dramatic in the strong gravitational fields surrounding black holes. Clocks running near the event horizon would appear to tick slower when viewed from a safe distance away. An astronaut falling toward a black hole would experience time passing normally from their own perspective. But outside observers would see their watch running increasingly slowly as they approach the point of no return. Near the event horizon, seconds stretch into hours, then days, then years from the external viewpoint. Astronomers detected this gravitational time stretching through careful analysis of X-ray emissions from matter spiraling into black holes. Hot material in accretion disks orbits at significant fractions of light speed just outside the event horizon. This material experiences extreme gravitational time dilation. The X-ray light from this material gets redshifted to longer wavelengths as it climbs out of the black hole's gravitational well. This phenomenon is called gravitational redshift. It provides direct evidence for time running slower in strong gravity. The most dramatic confirmation came from observations of star S2 during its closest approach to our galaxy's central black hole in 2018. Astronomers measured the gravitational redshift of light from this stellar speedster. This happened as it reached maximum velocity just 120 astronomical units from the black hole. The star's light showed precisely the wavelength shift predicted by Einstein's equations. This applies to objects moving through curved spacetime at relativistic speeds. Iron atoms falling into black holes provide even more detailed measurements of gravitational time effects. As iron spirals inward through accretion disks, it emits characteristic X-ray spectral lines at well-known frequencies. These cosmic atomic clocks show systematic redshifting that increases closer to the black hole. This exactly matches theoretical predictions for time dilation in curved spacetime. The universe's most extreme gravitational environments operate as natural laboratories. Time itself becomes a measurable experimental variable. Perhaps most remarkably, these observations confirm that time really is relative rather than absolute. There's no universal clock that ticks at the same rate throughout the cosmos. Instead, the passage of time depends on gravitational conditions and relative motion. This happens in ways that Einstein predicted but seemed almost impossible to believe. Black holes demonstrate that time itself is malleable. It stretches and compresses according to the curvature of spacetime around massive objects. Black holes operate the universe's most spectacular magic shows. They bend light rays around their gravitational fields to create cosmic optical illusions. These would impress any stage magician. These gravitational lenses don't use glass or mirrors. Instead, they warp spacetime itself to redirect light beams in ways that seem to violate common sense. But they follow Einstein's geometric theory of gravity with mathematical precision. The lensing effect occurs because massive objects curve the fabric of spacetime. Light always follows the straightest possible path through that curved geometry. Near black holes, spacetime becomes so warped that straight light paths curve dramatically around the gravitational center. From our perspective, the light appears to bend like laser beams passing through cosmic magnifying glasses. But the photons themselves never deviate from perfectly straight trajectories through their local spacetime geometry. Strong gravitational lensing near black holes creates multiple images of background objects. These are cosmic mirages that show the same distant star or galaxy appearing in different locations around the black hole's silhouette. The most extreme case produces something called an Einstein ring. It's a perfect circle of light surrounding the black hole where multiple lensed images merge into a continuous bright halo. These cosmic halos demonstrate spacetime curvature so directly that they provide visual proof of general relativity's geometric interpretation of gravity. Astronomers use gravitational lensing as a cosmic telescope to study both the lensing black holes and the background objects being magnified. The distortion patterns reveal details about the black hole's mass and rotation. They simultaneously provide enhanced views of distant galaxies that would otherwise remain too faint to observe clearly. Some of the most distant objects ever detected became visible only through gravitational magnification. Intervening black holes acted as natural cosmic telescopes. The lensing effects also create time delays that provide additional tests of relativistic physics. Light taking different paths around a gravitational lens arrives at Earth at slightly different times. This happens even when emitted simultaneously from the source. These cosmic light echoes allow astronomers to measure the precise geometry of spacetime around massive objects. They test whether changes in gravity propagate at light speed. As Einstein predicted, Perhaps most impressively, gravitational lensing reveals black holes through their absence rather than their presence. The Event Horizon Telescope detected the M87 black hole by observing its effect on light from the hot accretion disk behind it. This created a bright ring surrounding a dark shadow. The shadow itself represents the ultimate gravitational magic trick. It makes a 6.5 billion solar mass object visible by showing where it isn't. Black holes have created the most frustrating puzzle in modern physics. It's a problem so fundamental that it threatens to tear apart our understanding of reality itself. The information paradox emerges from an apparent contradiction between Einstein's general relativity and the principles of quantum mechanics. When these two most successful theories in physics disagree about what happens to information that falls into black holes, physicists get cosmic scale headaches. The paradox begins with a simple question that has no simple answer. What happens to information when it crosses a black hole's event horizon? Classical general relativity suggests that information disappears forever into the singularity. It gets completely removed from the observable universe. But quantum mechanics insists that information can never be truly destroyed. It might be scrambled or encoded in unrecognizable ways, but it must always remain recoverable in principle. Stephen Hawking made the paradox even more puzzling by discovering that black holes slowly evaporate through quantum radiation. Virtual particle pairs near the event horizon occasionally separate. One particle falls into the black hole while the other escapes as Hawking radiation. This process eventually causes black holes to shrink and disappear completely. But Hawking radiation appears to carry no information about the material that originally formed the black hole. This seemingly violates quantum mechanics' fundamental conservation principles. The information paradox forces physicists to choose between abandoning either general relativity or quantum mechanics. Both theories have passed every experimental test for over a century. Some proposed solutions suggest that information somehow gets encoded on the black hole's surface, rather than falling into the interior. Others propose that space-time itself breaks down near event horizons. This would invalidate the assumptions behind general relativity in extreme gravitational environments. Recent theoretical work has focused on quantum entanglement between particles inside and outside black holes. This suggests that information might escape through subtle correlations in Hawking radiation. But these quantum escape mechanisms require modifications to either general relativity or quantum field theory. These modifications haven't been experimentally verified. The cosmic headache persists because both theories work perfectly in their respective domains but predict incompatible outcomes when combined. The information paradox represents more than just an academic puzzle. It reveals fundamental gaps in our understanding of reality's basic operating principles. Black holes create natural laboratories where general relativity and quantum mechanics meet under the most extreme conditions possible. Until physicists develop a theory of quantum gravity that reconciles these contradictions, black holes will continue serving as cosmic professors. They teach lessons that nobody fully understands. Black holes represent the universe's ultimate graduate school for theoretical physics. They continuously assign homework problems so difficult that entire generations of scientists have struggled with them unsuccessfully. These cosmic professors don't provide answer keys. Instead, they challenge physicists to develop entirely new mathematical frameworks for understanding reality itself. The assignments keep getting harder as observational capabilities improve and reveal even more puzzling aspects of black hole physics. The firewall paradox represents one of the newest and most troubling homework assignments. Recent theoretical work suggests that either the equivalence principle breaks down near event horizons or black hole interiors contain walls of high-energy radiation. The equivalence principle is one of general relativity's foundational assumptions. The radiation walls would incinerate anything attempting to cross the boundary. Both possibilities require abandoning cherished principles that have guided physics for over a century. Naked singularities pose another unsolved cosmic homework problem. If certain rotating or electrically charged objects collapse past their event horizons, the mathematics predict naked singularities. These would form without being hidden behind event horizons. These naked singularities would represent points where space-time curvature becomes infinite while remaining visible from the outside universe. Most physicists hope that some cosmic censorship principle prevents such objects from forming. But nobody has proven this mathematically. The black hole interior represents perhaps the ultimate unsolved assignment. Nobody knows what actually happens inside event horizons. No information can escape to tell outside observers about interior conditions. The mathematics of general relativity breaks down at the central singularity. This leaves physicists to speculate about quantum gravity effects, alternative space-time geometries, or completely unknown physics that might operate in these hidden regions. Recent discoveries have added new homework problems to the cosmic syllabus. Gravitational wave detections reveal black hole mergers with unexpected mass distributions. These don't match current stellar evolution models. Some detected black holes appear too massive to form from ordinary stellar collapse. This suggests unknown formation mechanisms or exotic matter interactions. The cosmic professors keep assigning new problems faster than physicists can solve the existing ones. Perhaps most fundamentally, black holes challenge our understanding of what constitutes physical reality itself. If information that falls past event horizons becomes permanently inaccessible to outside observers, in what sense does it still exist? The cosmic homework assignments force physicists to confront deep philosophical questions. They concern the nature of existence, causality, and the relationship between mathematics and physical reality. Black holes operate as cosmic Zen masters. They pose koans about the nature of reality. They have no easy answers, but they force students to question basic assumptions about how the universe works. Stephen Hawking delivered the most surprising news in black hole physics in 1974. He announced that these supposedly eternal cosmic monsters actually evaporate slowly over time. Objects that seem powerful enough to last forever gradually shrink and disappear through a quantum mechanical process. This process is so subtle that it takes longer than the current age of the universe to become noticeable. The ultimate cosmic survivors eventually face their own mortality. The evaporation mechanism operates through one of the strangest phenomena in quantum physics. Even in completely empty space, pairs of virtual particles constantly pop into existence. They immediately annihilate each other in events so brief they barely qualify as real. Near black hole event horizons, some of these particle pairs get separated by the intense gravitational field. One particle falls into the black hole while its partner escapes to become real Hawking radiation. The escaping particles carry away tiny amounts of energy. They gradually deplete the black hole's mass according to Einstein's famous equation E=mc². Each escaped particle reduces the black hole's total mass by an infinitesimally small amount. The process resembles cosmic evaporation, where the black hole slowly loses mass energy to space one particle at a time. The ultimate cosmic vacuum cleaners eventually get cleaned out themselves by the quantum vacuum. Hawking radiation emerges as perfect blackbody radiation with a temperature inversely related to the black hole's mass. More massive black holes produce colder radiation. Smaller black holes generate hotter emissions. A black hole with our Sun's mass would have a temperature of only 60 billionths of a degree above absolute zero. That is far colder than the cosmic microwave background radiation filling space. These cosmic iceboxes radiate so slowly they are essentially frozen in time. The evaporation rate depends dramatically on black hole size. Stellar mass black holes lose mass so slowly that they would take 10 to the 67 years to evaporate completely. That is a time span trillions of times longer than the universe's current age. Even the smallest possible black holes would require more time than humans can meaningfully comprehend. Hawking's discovery revealed that black holes are not eternal, but their lifespans exceed anything in human experience by factors that stretch mathematical notation to its limits. The quantum evaporation process represents one of the most profound connections between general relativity and quantum mechanics ever discovered. Black holes operate as cosmic laboratories where Einstein's geometry meets Heisenberg's uncertainty principle. They produce effects that neither theory predicts independently. The ultimate gravitational monsters teach lessons about quantum physics that nobody expected. They reveal deep connections between gravity, thermodynamics, and information theory that continue puzzling physicists decades after Hawking's original insight. Black holes follow a cosmic longevity rule that seems completely backwards compared to everyday experience. In most situations, bigger objects require more energy to maintain and tend to break down faster than smaller, simpler systems. But black holes operate according to opposite logic. The more massive they become, the longer they survive. Meanwhile, smaller black holes burn out like cosmic candles. They evaporate faster and die younger in a cosmic mortality pattern that defies intuition. The counterintuitive relationship emerges from Hawking radiation's dependence on black hole mass. Smaller black holes possess higher surface temperatures and radiate energy much more rapidly than their massive cousins. A black hole containing Earth's mass would have a temperature of about 0.02 degrees Kelvin. It would evaporate in roughly 50 billion years, double the mass. And the evaporation time increases by a factor of 8. The cosmic mortality tables show exponential lifespans that favor gravitational heavyweights. Supermassive black holes enjoy practically eternal youth compared to their stellar mass relatives. The monster at our galaxy's center contains 4 million solar masses. It would require about 10 to the 87 years to evaporate through Hawking radiation. That is a lifespan so enormous that the number requires more digits than atoms in the observable universe. These cosmic senior citizens will outlast every star, every planet, and every other structure in the cosmos. They do this by margins that make geological time seem like brief moments. The size-lifespan relationship creates a cosmic hierarchy where the universe's most massive objects become its ultimate survivors, while stellar mass black holes evaporate in times comparable to cosmic epochs. Supermassive black holes will continue existing long after the last red dwarf star exhausts its fuel and fades away. The biggest gravitational monsters will inherit an empty universe. They will represent the only remaining organized structures in a cosmos filled with nothing but expanding space and cooling radiation. This mortality paradox also means that the universe's smallest black holes, if they exist, would be dying right now. Primordial black holes formed during the early universe with masses less than a mountain would be reaching the end of their Hawking radiation lifespans today. these cosmic fireflies would be exploding in final bursts of high-energy particles and gamma rays. They would create some of the most energetic events in the modern universe. Astronomers search for these cosmic death rattles as potential signatures of evaporating primordial black holes. The ultimate irony is that black holes grow stronger by getting bigger. This is directly opposite to mechanical systems that become more fragile as they increase in complexity. Cosmic natural selection favors the gravitational giants. It ensures that the universe's final chapter will be dominated by a few supermassive black holes, slowly evaporating in perfect isolation. They will outlast everything else by timeframes so vast they render all previous cosmic history insignificant by comparison. Tens of googles of years in the future, the universe will have grown cold and dark beyond imagination. The final supermassive black holes will stage the cosmos's ultimate fireworks display. After lifespans that dwarf all previous cosmic time, these last gravitational survivors will enter their final death spirals. They will accelerate toward explosive conclusions that will briefly illuminate an otherwise empty and frozen universe. These will be the most spectacular light shows ever witnessed. The final phases of black hole evaporation follow a dramatic acceleration pattern that builds toward explosive climaxes. For most of their incredibly long lifespans, black holes evaporate so slowly that the mass loss remains essentially imperceptible. But as they shrink, their Hawking radiation temperature increases. This causes evaporation rates to accelerate exponentially. The final moments happen remarkably quickly compared to the enormous lifespans that preceded them. A supermassive black hole's death throes begin when it shrinks to roughly stellar mass. This happens after googles of years of gradual evaporation. At this point, the cosmic senior citizen starts radiating noticeably faster. It loses mass at rates that become measurable on cosmic timescales. The acceleration continues as the shrinking black hole gets hotter and hotter. It radiates energy more and more rapidly in a runaway evaporation process. This builds toward an inevitable explosive finale. The final second of a black hole's life releases energy equivalent to millions of hydrogen bomb explosions. The last remaining mass converts entirely to Hawking radiation. The dying gravitational monster becomes a brief but brilliant beacon. It shines brighter than entire star clusters for the fraction of a second required to completely evaporate its remaining mass. These cosmic fireworks represent the universe's final energetic events. They are brief moments of brilliance punctuating eternal darkness. The explosions will illuminate a cosmos so different from today's universe that the comparison defies description. By the time the last black holes approach their final moments, all stars will have exhausted their fuel and faded billions of years earlier. All planets will have either fallen into dead stars or been flung into interstellar space as stellar remnants cooled to near absolute zero. The cosmic fireworks will shine on an audience of dead worlds orbiting corpses of stars. This happens in a universe expanded to densities lower than the best laboratory vacuums. Perhaps most remarkably, these final cosmic light shows represent the universe's last organized release of energy before heat death becomes complete. After the last black hole explodes in its terminal fireworks display, the cosmos will contain only cold, isolated particles separated by vast distances. Space will continue expanding and cooling forever. The final fireworks mark the end of cosmic history. They represent the moment when the universe transitions from merely old and cold to completely dead. No remaining energy sources will be capable of powering any form of organization or complexity.